In this exercise, we're going to apply the skills we learned about doing descriptive statistics and regression analysis with Python. And we have a new data set called the insurance data set. This insurance data set contains about 1,300 rows of data about insurance claims. So the insurance charges are given against attributes of patients such as age, sex, BMI, children, smoker, and region. So obviously, if you take a look here, you've got a couple of numerical variables, but there are also a couple of categorical variables such as, for example, sex, region, and smoker. In this data set, and let's first run this cell to load the data. We're reading this data from a CSV file. We want to do produce a descriptive statistics and the correlation matrix to get to understand, kind of roughly speaking, uh, what the data is about, the relationship between the different variables in the data. And then we want to use linear regression to predict charges. So charges is the main outcome here, and whether the insurance charges depend on these predictors that we've got in the data set. And then we want to interpret the results of the regression analysis. The goal of this exercise is to gain more insight about what leads to increased charges in medical insurance. All right, so let's start with the descriptive statistics. First, if you remember, Pandas has a very handy function to produce the descriptive statistics called describe. This function is going to produce the descriptive statistics for all of the numerical variables in our data. So for example, in this case, we've got age, BMI, children, and charges. Okay. Um, and the descriptive statistics that are produced are the count, mean, standard deviation, minimum, first quartile, median, third quartile, and maximum. Next, we want to produce the correlation matrix, and the function to produce the correlation matrix is the function CORR for correlation. And this function by default is going to produce the Pearson correlation coefficient. Very similar to describe, this function only applies to numerical variables, as you see in this case. Now, if you want to operate on the categorical variable, there are more advanced functions that you want to use, such as group by and aggregation. This is not something we will do this in this notebook, but we will going to look at those functions and the skills in the next part of this course, the second part of this course. Okay, let's examine the numbers here. So if you take a look at charges, the mean is 13,000, right? But you've got also a huge standard deviation. It basically says that there is a large variance when it comes to charges. And if this is the case, it's usually helpful to visualize the distribution of charges. And this is something we will do next when we learn about visualization. That's not the same for the other variables. The other variables have, except for children here, have standard deviation which is smaller than half of the average. So my guess here is that those variables are probably normally distributed, but again, we can't get to that conclusion without a visualization here. Interestingly, for children, we've also got a huge kind of variance, and that's probably skewed because of a couple of outliers, a few families that have 5 children. Okay, the correlation shows kind of the pairwise relationships between these variables. So we are interested in charges, and we see that they go with age, right? That's a positive correlation of almost 30%. BMI, 20%. They're not as related to children, which actually makes sense. Like in this case, they're a bit positively related to children, but not as much. And we've got the other correlations here. It's kind of that you can take a look at. All right. Next, we want to use linear regression to predict charges as a function of the other variables. And here we did not specify what variables, so you will need to use all of the variables that you've got in the data. In the introduction notebook, we use the function dmatrices to separate the data and into the outcome and predictor variables, and also to convert categorical variables to dummy variables. Today we're going to do things a bit differently. We're actually going to use a function that allows us to plug in the formula directly to stats model. So we're going to call the function the stats model OLS function to run an ordinary least square model. In this model, we're going to, instead of providing the y and x as we've done um, in the past, we're going to say that we want to estimate the models from the formula. And the formula here is going to be using the passive syntax, which is the syntax very similar to the syntax you type in R. So we're going to run charges as a linear combination of the other variables, and the other variables are going to be age, sex, let's take a look at, actually I'm going just to do data dot columns here just to show them. BMI, children, smoker, region. Obviously we cannot put charges, we're trying to predict charges. What's very handy with this function is that it's going to take care of converting the categorical variables into dummy variables. The only other parameters we need to pass is what is the source data frame. And the source data frame is going to be data. So the name of the data frame is data in this case. That's going to be our model. So I'm going to call the result of this variable model. If everything goes all right, we shouldn't get any error here. Okay, next we're going to get to the result of fitting the model to the data by calling the function fit, as we've done in the past. Before calling the function fit, we don't have results. Once we have these results, we can take a look at the summary. So we can do print result.summary, and that's going to print the summary of the regression analysis here. Okay, so again, main touch point, the R square is 75%, which is actually pretty decent, pretty good for this model here. Let me just make it a bit smaller so I don't get like text wrapping. Let's do it again. Fortunately, it's still wrapping the text. So let's try it a bit smaller. Okay, I think that's a bit better. So we can see also the coefficients here for all of the variables here. And what's interesting here is that before we go ahead and interpret these coefficients, we can take a look at the t-values and the p-values. So it looks like everything except male and northwest is statistically significant. It's basically saying that for a smoker compared to non-smoker, on average, you get much more charges. Basically, that's 2.8 with 4 zeros to the right, so that's 23,000 more for smokers in terms of insurance charges compared to non-smokers, which is a big difference. And we see that, for example, northwest, southwest, southeast, and southwest, they have negative coefficients. What does that mean? Well, when you've got dummy variables, you only interpret the results compared to a baseline. And the baseline here is the northeast because it doesn't show here. So compared to the northeast, northwest has on average a claim from the northwest is $352 less on average, holding everything else constant, although that difference is statistically non-significant. So it means that northwest is very similar to the northeast, but when it comes to the southeast and southwest, they are the charges are lower than the northeast, and the difference is statistically significant. Same thing for male compared to a female. You've got on average $131 less in male insurance claims, although that difference is statistically non-significant, which basically means there is no difference, no particular bias in terms of charges in between male and female patients. Um, age, you see that with age, with each extra year, we've got $256 increase in medical insurance claims on average. And same thing with BMI, each point in BMI results in more charges. And the same thing with children. Though for children, I'm not sure whether this is related to treating the children or patients with children happen to have more medical problems and more higher medical insurance claims. So kind of that's roughly speaking, give us the statistical model an idea about um, what drives medical insurance claim cost. And it's getting us to some interesting insights from this data. Finally, we can, if we wish, just look at the parameters. We can look at the parameters individually, or we can look at the R square. We can do some visualization, although in this case, it's not kind of requested.